So laser metal deposition is a process that belongs to the additive manufacturing technologies, and in particular to the processes of direct energy deposition. In direct energy deposition, the material and the energy source, like in plastic 3D printing, are delivered through a nozzle. But most commonly, these technologies are used for metal components. The metal is usually delivered in form of powder or wire, and then it's melted through with the use of a laser in laser metal deposition, or also plasma and electric current are commonly used as well. Through a pre-programmed motion between the nozzle itself and the substrate, the material is added in a layer-by-layer way and then solidifies to recreate a 3D geometry. As mentioned before, laser metal deposition is mainly used for metal components, and most commonly it is used to print steel, titanium or nickel-based alloys. With aluminium, on the other hand, there are more challenging factors concerning mainly the material quality assurance and geometrical accuracy of the process. Regarding material quality assurance, the main issue is the reactivity of the molten aluminium with hydrogen and oxygen present in the atmosphere, and that is why often it is printed under inert atmosphere condition. This reactivity with hydrogen mainly leads to the presence of pores and cracks within the solidified material. Regarding geometrical accuracy, on the other hand, aluminium has very low heat dissipation capability and melts at very low temperature compared to other metals, leading to longer solidification time, and the molten metal can spread into a wider area, and this is hard to control the geometry into which the aluminium solidifies. There are a lot of different parameters that influence the laser metal deposition process, and they mainly depend on the system that we use and the material that we want to print. However, when we optimize a process for a specific components, we have three parameters that we identify usually as the most important one, and they are the laser power, the deposition speed, and the amount of material that we feed through the nozzle. Laser power mainly influences the temperature of the melt pool that we create and the solidification time needed by the material. The deposition speed, on the other hand, determines the cooling rates the material is subjected to, and therefore the microstructure of the part at the end, while the amount of material that we feed through the nozzle mainly influences the geometry of the track and the ratio between the height and the width of each track that we deposit.